Hello student, welcome to the one more session of embedded microcontroller and embedded system. This is Vasan Nayak from Canara Engineering College. In this session, we will see the core of the embedded system. That is, what are the core components or brain components used inside the embedded system. So, other than that, here we will discuss first of all the core components of the embedded system, like processor, microprocessor, microcontroller, microprocessor, microcontroller, digital signal processor, normally which is used to deal with the data like multimedia data like audio, video, and we also discuss application specific integrated circuit, then application specific standard product. Other than that, we will discuss here the different types of memory, input output device, sensors, actuators, then various communication interface which is used in embedded system. So you can see from the diagram, this is the core of the system. This controller can be either microprocessor or microcontroller or FPGA, that is field programmable gate array, or it can be digital signal processor, or it can be application specific integrated circuit, or it can be application specific standard product, so and so. So this is the actually main controller of the embedded system. So basically, embedded hardware and software basically designed to regulate the physical variable or manipulate the state of some variable by sending some control signal to the actuator or devices connected to the output port. So here you can see we have input port. To the input port we have connected sensors. That means sensor will going to connect, sensors are connected to the input port, and which sensors will take the input from the external world and it will pass that input to the corresponding electronic circuit, and in the output you can see the actuators are connected to the output, and the output device also you can see we connect here LEDs, buzzer, so and so. So other than that, so if I want to give the example for input device, then input device are like keyboard, then push button switches, and output device are LEDs, then liquid crystal display. Other than that, electronic buzzer, all those are the output device. Similarly, we can see here like memory, a small memory which is responsible for holding the controlling algorithm or logic. Based on this logic, this embedded system will work, and the other configuration details. So what actually this memory contains? This memory contains actually embedded firmware. I told in the previous video the difference between firmware and software. Firmware means it is a software permanently stored, it cannot be reprogrammed. So it cannot be reprogrammed. Other than that, you need to connect this embedded system to the external world by means of communication interface. So how do I make my embedded system core can communicate with the external world by means of a communication interface. This contains USB communication, other than that TCP/IP communication, Wi-Fi communication such as wireless communication such as Bluetooth, Zigbee, etc. So we have other supporting integrated circuit, for example brownout circuit, which is used to reset the embedded system when the input or output voltages goes below certain threshold value. So this is the actual various functional parts of the embedded system. So the controller can be, as I said earlier, it's a microprocessor like Intel 8085 or like different types of microprocessor, microcontroller, or field programmable gate array FPGA device such as Xilinx or Spartan. So when it comes to field programmable gate array, it's a programmable logic device which can be reconfigured to perform any function by software. The great advantage of this field programmable gate array is that the chip is completely programmable and can be reprogrammed. It has got many planes of millions of AND gate, NOT gate, OR gate. All these are controlled by software, programmable by software. Other than that, we have something called a digital signal processor, which basically used to modulate the data which is related to multimedia. Then you have something called as application specific integrated circuit, which is meant for particular application or particular hardware. Other than that, we have application specific standard product like AD7760's IC, which is used in single phase energy metering meter, which will actually calculate the power consumption in the electrical meter, which is used in the household application. So the difference between ASCII and ASP is ASCII is proprietary. That means it is not available in the open market. Application specific standard product, it is not non-proprietary. That is, it can be sold out in the open market. So the main purpose of the embedded system is embedded system consists of hardware and software, and basically designed to regulate the physical variable to manipulate the state of some device which is connected through input or output. Normally input is input is connected to the sensor and output is connected to through actuator, and we have the memory which is responsible for holding control algorithms and other logics. So now we will discuss one by one the core of the embedded system. First we will see in the core of the embedded system, first we will see the controller. Controller can be, as I said, it can be microprocessor, microcontroller, digital signal processor, or as I said ASCII says this one IC, or programmable logic device, or sometimes commercial off the shelf components, COTS. So these are different types of the controllers are used here. So now first one is a microprocessor. We know what is a microprocessor. Microprocessor is integrated chip which can process the data with the help of control unit and ALU, and which has got a small memory which can store the set of instructions. So my CPU contains arithmetic and logic unit. So different types of CPUs are available in the market. So in the first CPU was from Intel, was 404, which was a 4-bit microprocessor developed in 1971. Intel 8080 was came into the market in the year of 1975. Simultaneously, at the meantime, Motorola developed something called as 6800 with different instruction architecture compared to Intel. In the next version of the Intel 8080 was 8085, which is the 8-bit microprocessor. So in July 1976, Zilog entered into the market with its own processor called as Z80 processor as a competitor to the Intel. So these are the different vendors. They are the key players in the processor market, like Intel, AMD, Cyrix, Nvidia. All these are the different players. They play key role in the processor market. So now we after talking about microprocessor, now we'll see microcontroller. You know the difference between microprocessor and microcontroller. So microcontroller is a highly integrated chip which has got both CPU and RAM, ROM and other input and output ports, etc. So it has got one board ROM, RAM, flash memory and dedicated input and output port. So microcontroller contain all the necessary functional blocks for independent working. Microprocessor doesn't have all the blocks for independent working. So if you see the history of the microcontroller, the first microcontroller was from Texas Instruments, TMS 1000 in 1974, and first microcontroller first microprocessor or microcontroller from Intel was 404 4-bit processor, which is used in calculated design, which is a calculator is nothing but embedded system. Then in 1977, Intel came with the 8051. It is a 8-bit microcontroller. So next one is 8051 processor. Cores are used in more than 100 devices by more than 20 independent manufacturers like Maxim, Philips, Atmel, etc. The one major key factor for the use of this microcontroller was low cost and widely available and memory efficient instruction set, mature development tools and Boolean processing, that is bit manipulation operation. So 8051 family derivative microcontroller are much used in high volume consumer electronics and entertainment industry. Now we will see couple of points related to the difference between microprocessor and microcontroller. Already we are aware of this one. Microprocessor generally doesn't have RAM and ROM IO pins. Microcontroller have ROM and RAM and IO port all on the chip. Microprocessor usually use its pins as a bus to interface to RAM and ROM. Normally RAM and ROM, all these memory devices should be interfaced to the microprocessor, but here it is internal. That's why the circuitry design of the microprocessor becomes somewhat complicated. Microprocessors are generally capable of being built into bigger general actually it is microprocessors are used to build general purpose application, but microcontrollers are used for specific application. And because of the so many components used, so many components are interfaced to the externally interfaced to the microprocessor. They don't have power saving system, but microcontrollers have power saving systems. It's built in. So the overall cost of the microprocessor systems are very high. The overall cost of the microcontroller systems are low, but speed of the microprocessors are in terms of gigahertz above 1 gigahertz. But the processing speed of microcontroller from which ranges from 8 megahertz to 50 megahertz. And one more thing is microprocessors are based on one human model. One human model means where is only one memory is used for program and data. But that means program and data are stored in the same memory. But in microcontroller, the program is microcontroller is based on, most of the microcontrollers are based on something like ARD architecture, where program memory is different and data memories are separate. Now we will see the digital signal processor. These are the powerful special processor like 16-bit, 32-bit microprocessor designed to meet computational demands of computational demands. Especially it is used to deal with the data related to audio and video, especially the data related to multimedia. So digital signal processor are 2 to 3 times faster, and DSP implement algorithms in hardware. That's why it is faster. So DSP can be viewed as a microchip designed for performing high-speed computational operations like addition, subtraction, multiplication, division, etc. And so what are the basic components, like what are the basic functional parts of or key units of digital signal processor? The digital signal processor contains program memory, which holds the program, then data memory, which is working memory for storing temporary variables, then computational engines, which is actually performs the signal processing in accordance with the instruction, then which has got IO unit, acts as interface between outside world and DSP. So you need to understand one thing here. So digital signal processors are used in audio video signal processing, telecommunication and multimedia application. Digital signal processing employs large amount of real-time calculations, like sum of products, SOP, we know that one. Then fast Fourier transform, then discrete Fourier transform, etc. All these type of calculations are performed by digital signal processor, which are necessary when it processes the multimedia related data, audio and video data. Now next category of the processor are RISC versus CISC. So the full form of RISC is reduced instruction set computing, and the full form of CISC is a complex instruction set computing. So most of the microcontrollers are based on the RISC, but ARM has adopted the property of both RISC and CISC. So now all the RISC processors process less number of instructions, but CISC stands for complex instruction set computing, and it processes complex instructions. So now we see the difference between CISC and RISC. Like you see here, the complex instruction and taking multiple clock cycles, like CISC instructions are taking multiple clock cycles, like various type of instruction, like 1 byte, 2 byte, 3 byte, 4 byte, 5 byte, 6 byte, like that. Here CISC instructions are like simple instructions and taking single clock. For example, if you say take ARM7, all instructions are 32-bit, 4 bytes and taking single clock. Almost all instruction. Here emphasis on the hardware, complexity is on the micro program processor. Here the complexity on the software. So complex instructions are executed by the processor. Here reduced instruction means it is not like less number of instruction. We can say there is there won't be a multiple form of same instruction. For example, if you take CISC processor, then there is a instruction. Suppose if you consider add instruction, there is a add instruction for register operation, and there is a add instruction for memory related operation. If you take ADC, add with carry, there is a add with carry instruction for register related operation, and there is a add with carry instruction for memory related operation. But same thing with RISC operates most in the RISC processor. It operates on load and store architecture. Load and store means most of the operation will be carried out in the register rather than in the memory. That's why there will be only one form of instruction than the multiple form of instructions. And because of variable format instruction, single register set and many instructions, here variable format instruction, here fixed format instruction. Because of the different different instruction related to memory as well as register. In CISC there are different addressing mode, but in RISC there are fixed and few addressing modes. So here memory reference is embedded in many instructions. Here memory reference is embedded in only load and store instruction. That is the difference between a CISC and RISC. And one more thing is CISC and RISC emphasizes the different types of memory architecture. That is, one is RWARD, other one is von Neumann. I have told already what is the von Neumann. Von Neumann architecture, like both the data and data and instructions I mean stored in the same memory, but in AWAD architecture there is separate memory for data, separate memory for the instructions. So most of the microcontrollers are based on like von Neumann architectures. Most of the microprocessor and microcontroller are based on the von Neumann architectures, but RISC processors are based on AWAD architectures, but ARM makes use of both. Now you can see here the difference between AWAD architecture and von Neumann architecture. Here you can see single shared bus between memory input output, but here you see there is a separate bus for program memory and there is a separate bus for data memory. So if you see the difference between von Neumann architecture and AWAD architecture, single shared bus for the instruction and data, separate buses for the instruction and data patching. Chances of accidental corruption of program memory. Chances of accidental corruption, there is a lot of chances of accidental corruption of program memory, as the data memory and program memory are stored physically in the same chip. But here no chances of accidental corruption of program memory and data memory, because they are stored in the different locations and different chips or different locations. Low performance compared to the like here it is a low performance compared to the AWAD architecture, because both data and this one are stored in the same memory, that's why low performance. But here it is a performance high because it's easier to pipeline, high performance can be achieved. Then here so here some memory alignment problems are there, but in this architecture there is no memory alignment problem. Now we need to understand what is the difference between big endian and little endian. So we you call this as a big end and a little end. So normally this actually specifies the order in which data is stored. So in case of little end, if you see this is the lower address, so we have lower address 20,000, 20,001, 20,002, 20,000. This starts from 20,000, 20,001, 2, 3, 20,000 the base address. Then we have 4 byte of data, that is the LSB is byte 0, byte 1, byte 2 and byte 3. Then lower byte is stored in the lower address, higher byte is stored in the higher address. This is related to little end. What about big end? So in the big end you see here, so address is once again like this is the base address 2001, 2002, 2003, but we have byte byte 0, byte 1, byte 2, byte 3. So lower byte is stored, you see here lower byte is stored in the higher address and higher byte is stored in the lower address. So this is the difference between little end and big end. This indicates the order in which data are stored in the memory. So next one is load, store, operation and instruction pipelining. RISC processor instruction set is orthogonal. RISC processor instruction set is orthogonal, means it operates on registers. Most of the time in the RISC processor operates on the register. So memory related operations are very less. For example, if you take ARM7 operates 90% of the time ARM instructions operates on the register, like load and store is used to fetch the instructions from the memory, but whatever the operation, it will be performed in the register only. So there is no operation will be performed on the memory. That's why RISC processors are rigid, but it is faster. So the memory access related operation performed by special instruction load and store in the RISC processor. So here this architecture shows how load and store operation takes place. Suppose we have 3 memory location X, Y, Z. These are the 3 memory locations and we want to add the content of X and Y and store the result in Z. So this is X, Y, Z, 3 memory location, and these are the data in the 3 memory locations. These are the like these are the data, like x in the location x contains 0 0, in the location y it contains 7f. So in the RISC processor, what it will do is it will first load the content from the memory to the register R1, that is, this content is loaded here, this content is loaded here, like in the second instruction. Then it will add register R1 and R2 and store the result in R3. Finally store the content of R3 in the memory by using load and store operation. So load is used to load the content from the memory to the register, and store is used to store the content back to the memory. So only the two operations works on the memory, that is load and store. Rest all the operation works on the register. So we need to understand here, conventional instruction execution by the processor follows fetch, decode and execute. Fetch means this part will fetch the instruction from the program memory or code memory. Decode means it will analyze the instructions and sends the necessary signal, control signal, to the various functional unit. Execute means stage reads the operands, perform the ALU and ALU related operation and store the result. So in order to improve the performance, ARM RISC processor, RISC controller makes use of pipeline. Pipeline will improve the performance. Now we will move to the next component, that is application specific integrated circuit. As I told earlier, the application specific integrated circuits are meant for particular purpose. Like it is designed for particular purpose. This chip is designed for particular application. So one thing you need to remember here, these application specific integrated circuits are like proprietary. This is designed for particular application, particular design, something like that. It cannot be sold in the open market. So what this chip will do? This integrates several functions into single chip and thereby reduce the system development cost. So this chip contains several functions into single chip and reduce the system cost. So it will consume less power also and less area also. ASCIIs can be prefabricated on a special application, or it can be custom fabricated by using components. So it is a custom design. So what are the features of the ASCII and what are the drawbacks of ASCII? So the features of ASCII are NRE, that is non-recurring engineering charges, that is one-time expenses for the process, technology and configuration expenses. Then less complex, the circuit is less complex because it is actually designed for particular function, no need to include several functionality, then which can give high performance and low power consumption, because circuit content like this IC contains a required amount of circuits for the particular function. That's why these are the advantage. Then drawbacks is inflexible design. Like this design is meant for particular application, so it cannot be flexible. Updates requires redesign. In the case I need to update the particular this one, then I need to redesign it. Deployed system cannot be upgraded. For example, if I deploy this one, if I adopt this in particular design, that design cannot be upgraded. You need to go for a entire redesign, complex and expensive development tool. So since it is meant for particular applications, so particular tools are required and those tools are complex and expensive. Mistakes in product development are costly. Suppose if any mistakes happens in the product development, which are costly. So next, other than that, so here is the difference between application specific integrated circuit and application specific standard product. Actually, ASCIIs are microchip designed to perform specific application, and most of the ASCIIs are proprietary product, as I told earlier. But if the third party is ready to pay NRE cost, we know what is NRE, non-recurring engineering charges, and ASCII is made available into the market, open market, then ASCII is referred as a ASSP, that is application specific standard product. So normally this is available, openly available in the market. Now next one is we need to see the difference now, various difference between different type of processor. First one is a general purpose processor versus application specific instruction set processor, ASIP. We know GPP is a processor designed for general computational tasks like Pentium 4, AMD, etc. GPP contains arithmetic and logic unit and control unit. ASIP are the processor with architecture and instruction set optimized for specific domain or specific application requirements. So next we have something called as a programmable logic device. So by using programmable logic device, you can implement various functions. So including device to device interfacing, data communication, signal processing, almost all these can be implemented. So there are two categories of programmable logic device. One is called a fixed, second one is a programmable. So FLD offers customers a wide range of logic capacity, speed and voltage characteristics. Now we'll see what are the two different types of FLD. So first of all, before moving to two different types of FLD, what are the advantages of FLD? Programmable logic device offer a number of advantages over the fixed logic device, including FLD offer customer much more flexibility. Then second, don't require long lead time for prototypes production. Don't require customer to pay for a large NRE. Allow customers to order just the number of parts they need. Reprogrammed even if a piece of equipment is shipped. So all these are the different types of advantages. Now, so there are two types of FLDs. One is field programmable gate arrays. I told what is this field programmable gate arrays. Other one is complex programmable logic device. Actually this one FPGA is a programmable logic device which can be reconfigured to perform any function by software. This has several planes, and each plane contains of millions of like gates, like AND gates, OR gate, NOT gates, and all these can be programmed by using software. Great advantage of FPGA is that chip can completely programmable or reprogrammable. Second one is the complex programmable logic device, CPLDs. So here are the difference between the CPLDs and field programmable gate arrays. Let me read out one or two. PLDs are used to construction of CPLDs, but logic blocks are used for the construction of FPGAs. CPLD is non-volatile and less costly. FPGAs are volatile and costly. We know this one. And there are some other differences like prediction of delay is difficult in FPGA. Operating speed is high and is suitable for timing circuit, but here operating speed is low. All these are different types of differences. Similarly, we have differences between FPGA and ASCIIs. FPGA is reprogrammable. ASCIIs are unique type of integrated circuit. FPGA is not efficient in terms of use of materials, but ASCIIs wastes very little material. FPGA is better than ASCII when building low volume production circuit. Cost of ASCII is low only when it is produced in larger quality. FPGA is alterable. ASCII cannot be alterable. All these are the difference between FPGA and ASCII. Then the last one is commercial off the shelf components, COTS. See, actually COTS is the product which is the other name for this one is used as is. Use it as it is. COTS for products are designed in such a way that which can be easily integrated in the other existing system without any modification. And cost component may be developed around the general purpose domains or specific purpose or application specific integrated circuits. So, for example, you can see here different types of the for example the example of COTS. This one. This is the actually the circuit or the simple PCB design. Suppose this can be, suppose if I want my embedded system to have a connection, LAN connection, then this can be, I can connect this to the existing embedded system by simply knowing the signals of the various pins without modifying this board or the existing embedded system. So here I can connect my LAN signal through TCP/IP. Like this type of cords are easily integrated in the embedded system without any modification. So cords are cheap, cords are readily available in the market. Developer can cut down his or her development time to greater extent. So I told what are the examples like TCP/IP plugin module available from the various manufacturers that can be used as shown. Then the benefits of the cost-based system: reduce the development cost, to improve the memory software development process, to reduce the software life cycle. So all these are the different types of advantages. So with this, I will wind up this session. So in the next session, we will see the memory and different configurations related to the memory. Thank you.